given a domain D, we are going to say that it is simple connected if it is connected and every loop in the space can be contracted to a point in the space. So, for instance, this space that is here will be simple connected, but if we have a space like this, for instance, they have a hole here, so we have like the space is just this part here. This space is still connected, right? I mean, between 2 points, there is always a path between them. Between 2 points, there is always a path in the space. But not every loop here can be contracted continuously within the space. So, for instance, let's consider a loop like this. So no matter how do we try to contract, this loop will be always outside of the domain. So a domain like this is not simple connected. Let's consider now a version of the fundamental theorem of calculus, but now for line integrals. If we have a curve C between A and B, and we have a vector field such that is conservative, meaning that it comes from the gradient of certain function, certain potential function. So in this hypothesis, we are going to say that the line integral of the vector field is going to be equal to the potential function evaluated at B minus the potential function evaluated at the beginning of the curve. See that here the potential function plays the role of a primitive of a function. So let's see how do we use this theorem in practice. Be sure that in order to apply this theorem, we have to have here a vector field that is a gradient one. I mean, that is a conservative vector field. Let's calculate the line integral of the vector field f, where the vector field f is the gradient of this function. So if the vector field is the gradient of this function, so we already know that what function is the potential, right? The vector field f first. So the vector field f is the gradient of f. F is this function, so the gradient is going to be the derivative respect to x here is just 1. The derivative respect to y, so here will be 0, and here the derivative respect to y will be just z. And the derivative respect to z is going to be 0 and y. So this is the gradient of small case f, and this is then capital F, right? This is the vector field that we want to calculate the line integral. We have two ways to calculate this. The way that we already knew, I mean applying the definition of line integral, and the way provided by the fundamental theorem, that is simple, calculating the potential and evaluating at the beginning and at the end of the curve. So in this case, we are going to consider the curve C is going to be a semicircle in the xy plane. This is Z of radius 1 that goes from here to here. Okay, so we have two ways to calculate this integral. Let's calculate it first as we already knew it, just by the definition of line integral. So we know that the line integral C dr, in order to calculate this, so first we need to parameterize the curve. So in this case it's a circle, so we know that the parameterization of this circle is going to be cosine t sine t 0, right, since the curve is contained in the plane of the floor. Okay, so and we know that the t is going to be varying between 0 and, in order to get to that point, will vary between 0 and pi. Okay, so in order to calculate the integral by the previous method, I mean just by the definition, we are going to need to evaluate the vector field at the parametrization of the curve, and also we need to calculate the derivative of the curve. So let's calculate the derivative of the curve. The derivative will be minus sine t, derivative of sine is cosine, and derivative of 0 is 0. And the vector field evaluated at the curve, in this case is 1, there is nothing to evaluate there, so it will be just 1. The second one is z, so evaluating at here, so we see that z is actually 0, so this is going to be 0. And the third one is y, evaluating here is going to be sine t. Okay, and so once that we have everything that we need for this dot product, we perform the dot product, right? So this will be the integral between 0 and t, 0 and pi, and we do the dot product of these two vectors that we calculate here. So that will be, let's write down the vectors here first, 1, 0, sine t, dot product, and the other vector is minus sine t, cosine t, 0. And that will be dt. So this is the integral between 0 and pi of, let's do now the dot product. This is 1 times minus sine of t, this is minus sine t, plus 0 times cosine, this is 0, plus sine times 0, this is 0. So what we have is the integral between 0 and pi of just minus sine t dt. We integrate, the integral of sine is minus cosine, with a minus in front, it's just cosine t evaluated between 0 and pi. So we do the operations here, and this is minus 1, minus 1. So the final answer is minus 2. Okay, so let's now calculate the same thing by the second method. I mean, the method that this theorem provides. The second method says that all what we need to know is what is the potential. I mean, what is the function that this vector field is the gradient of. Well, in this case, the function we haven't given here. So this is the only function that we need. So we don't need any parametrization of the curve. The only thing that we need to know is where the curve starts and where the curve finishes. So in this case, we know that the beginning will be this point here, that is the point 1, 0, 0, right? So this is the beginning of the curve, and the end of the curve will be minus 1, 0, 0. So that is all what we need to know, because the integral over CF dr, according with the fundamental theorem that we just learned, is equal to the potential, that is the function given here, evaluated at B minus the potential evaluated at A, at the first point. Let's evaluate the function at B first. B is minus 1, 0, 0. So we are going to plug in here minus 1, 0, 0. And the result is going to be minus 1 plus 0. So that is f of b. And then we have to subtract, and we are going to write now f of a. A is 1, 0, 0. We have to evaluate here. This is 1 plus 0. And so at the end of the day, we get minus 1, which is minus 2. You see that if we actually have this function f, the potential, is much easier to calculate this way than to calculate actually by definition. That is the only tool that we used to have. But then, so this is possible to do. I mean, it's possible to do this way that is much easier only when the vector field is actually the gradient of something. So in this case, we just calculate the vector field as the gradient of the function, so that's why we knew that was the gradient. But in general, we may have a vector field that we don't know if it's actually the gradient of something. So if it is, if we know that this vector field is conservative, the way to calculate the potential function, I mean, what is this function that this is the gradient of, is going to be given by this method that is based in the fact that the cross derivatives of the vector field, if the vector field is conservative, have to coincide. So using that, we are going to integrate the first component of the vector field with respect to x. And so integrating with respect to x means to consider y as a constant. And so when we finish the integration, when we put an m plus constant, in our case, this constant could eventually depend on y. So the result of this step is going to be certain function, which is a primitive of the function m, plus a function, unknown function that depends on y. And so the objective of the method will be to find out what is that function h, because when we find this function, so this will be directly then the potential function. Okay, so once that we do then the integral of this with respect to x, we end up with a function like that. And then what we are going to do with that function is to take the partial derivative with respect to y. So that's what we do in the second step. We take the function from the previous step and do the derivative with respect to y. Well, if this vector field is conservative, that should be just the second component, right? So that is the equation that we are going to set up. The derivative with respect to y have to be equal to h. And so by setting this equation, we can find out how much is h prime. And so once that we know how much is h prime, then we integrate h prime to find h, to find the primitive of h prime. And once that we have h, so then it's going to be the potential function. Now let's consider this conservative vector field. Let's assume that we know that is conservative. We will see in a moment why it is. But let's assume that it's conservative, and let's just apply to practice the method. Well, the method, what it says is that first of all, we have to take m, I mean the first component of the vector field, and integrate it respect to x. So this is going to be our first step. We are going to integrate m respect to x. In this case, this is the integral of all this, right? The first component. So to integrate this, remember that we are considering y as a constant. So the integration of the first term will be 4y to the 4. This is a constant, goes out, right? And we integrate just x cubed. That is going to be x to the 4th power over 4. And then plus, we are integrating this respect to x. This is x squared, right? So 2x squared over 2, which is x squared. And plus a constant, but in this case, remember that we are integrating respect to x, so this constant may depend actually on y, because y is considered the constant now. Okay, so this is then the function. Let's do just a quick simplification here. And so this is the function that results from the first step. This is going to be essentially the potential function, right? Once that we calculate how much is h. So we continue with the second step in order to calculate h. The next step is to take this function and do the derivative respect to y of this function, right? The one that we obtained in the previous step. So let's calculate the derivative of this function with respect to y. So now x is going to be considered constant. So this is a constant. So this is going to be x4, that is a constant that goes out. And let's do the derivative of y to the fourth power, which is 4y cubed, plus the derivative of x squared. Well, x squared is a constant with respect to y, right? So then this is 0. And plus the derivative of this with respect to y, which is just the derivative of this function. Okay, so we found this function. Let me write it down. Beta just 4x4y cubed plus h prime y. So this is the result of the second step. And so these have to be equal to the second component of the vector field. That's the equation that we are going to set up in the third step. So we are going to say that whatever we obtain, in this case is this, has to be equal to n, right? So the second component of the vector field. Okay, solving this equation, we see that this cancels with this. We get from here that h prime of y is equal to y. And so from here, the next step is, once that we have the derivative of h, the next step is to calculate h, the primitive. Well, h is going to be just the primitive of h prime, y squared plus a constant. And so we finally got how much is h. Knowing how much is h, we come back here, and that will be the result of our potential function. So the potential function then, f depending on xy, is going to be this, which is x to the 4, y to the 4 plus x squared plus h. But h now is this, so which is y squared plus k. So this is a potential function for this vector field. And if we are not sure, if maybe we did some operations, some mistake in the operations, well, a very obvious check here is to actually calculate the gradient of this. So if you calculate the gradient of your potential, you should obtain what you started with. So we said at the beginning, let's assume that this vector field is conservative. Well, we can actually assume, we can know that actually this is the case because of this version is a kind of partial reciprocal theorem of the one that we have seen already. Remember that we knew that if the vector field is conservative, then these two things coincide. Well, what we are going to say now that this is actually the reciprocal is also true in case that the domain is simple connected. So if we have a domain like this, like that is simple connected, so in a domain like this, we can say also that the reciprocal is true, that if the vector field satisfies that these two things are the same, so then it's going to be conservative. So in the case of simple connected domains, we have like if and only if theorem. So the vector field is conservative if and only if these cross derivatives are the same. So we can easily check that in this case, that's what happens. We do these cross derivatives, they are both the same.